En equal to 1, it is disabled, else it will not be disabled. And whenever the gates are enabled, you cannot tell the output as long as you know the other inputs. Okay, remember this. So if logic gates are disabled, you can tell the outputs. You can just say NAND gate disabled, output is 1. If NOR gate is disabled, output is 0. And when the NOR gate is disabled, if any one of the input is 1. Okay, so this enable disable concept is very important and will form the basic foundation for to understand, okay, all the memory elements, that is latches and flip flops. So just remember that enable disable concept. Now just here s equal to 0, or what I'll do is, yeah, fine, I'll start with this, I'll start with the second combination just here. S equal to 0, R equal to 1. Look at here, S equal to 0, this is the input, R input is 1. So these two inputs, S equal to 0, R equal to 1 again. Now R equal to 1. Now out of these two NOR gates, which NOR gate is disabled? You have to identify the NOR gate which is disabled first. Focus on the gate which is disabled. So just here R equal to 1. This gate will be disabled. Just now I told you. Okay, for NOR gate, disabled means any one input should be 1. So here you can just here, this NOR gate 2 is disabled. Or what I'll do is, I'll just make one more table, so that I'll just add this Q1 plus 1, NOR gate 1, NOR gate 2. See, NOR gate 2 is disabled. NOR gate 2 is disabled because one of the input is 1, and NOR gate 1 is what? Enabled. You can just say S equal to 0. Just now I told you what is enable disable concept. NOR gate will be disabled if any one of the input is 1. R equal to 1, NOR gate 2 is disabled. Now when NOR gate 2 is disabled, output will be by default equal to 0. Sorry, this ED. So this is the second row I am taking. So E, this is D. E for enable, D for disable. NOR gate 2 disabled, NOR gate 1 enabled. These are notations I am using. E for enable, D for disable. So NOR gate 2 is disabled. So when NOR gate 2 is disabled, output will be what? 0. Output will be 0. That means previously the bit can be anything. That means before giving the inputs, the output, the output Q can be 0 or 1. It doesn't matter to me. But after giving R equal to 1, S equal to 0, after giving inputs means Q1 plus 1 I am talking, then definitely it has to be 0, because what? NOR gate 2 is disabled. So Qn plus 1, the next value, okay, should be 0 at any cost. It has to be 0. Previously it can be anything, because I have given input. After giving inputs, it is called Qn plus 1. Just now I told you. Now see the next one. S equal to 1, R equal to 0. So next combination, just look at here carefully. S equal to 1 I have given, R equal to 0 I have given. Previous value I am not bothered. Okay, previous value, let it be 0, 1, whatever it is. S equal to 1, R equal to 0. Now you focus which is disabled, which is enabled. S equal to 1 means NOR gate 1 is disabled. NOR gate 1 will be disabled. So if NOR gate 1 is disabled, Q bar, the output of this gate will be automatically 0. And remember, Q bar is 0 means, look at here carefully. So this Q bar is actually connected to what? Okay, NOR gate 2 input. So this, at this point, it will be 0. So 0, 0 are going inside the NOR gate. 0 plus 0 whole bar is what? It will become 1. You can just say Q is 1 means Q bar has to be 0. Both are complement. So correct combination. So what is the value now? That means after giving the inputs, the next value what the device will store is, it is 1. Next value means it is 1. So this enable, that's it. Previously you take whatever the bit, but after giving the inputs, definitely this will be 1. Okay, from this enable disable concept. Now let us see the first one. S equal to 0, R equal to 0. S equal to 0, R equal to 0. I don't know what is the previous value. Previous value can be anything, whatever, I don't know. After giving the inputs means it is always next value I am talking about. So S equal to 0, let us say first, let us take the first combination. S equal to 0, R equal to 0. So if both are zeros, what will happen is the NOR gate 1 is enabled, NOR gate 2 is also enabled, because if any one of the input is zeros, okay, NOR gate will be enabled. Now just here, so if both are enabled, let us see what will be the output. If R equal to 0, if it is enabled, I told you that the output will depend on the other input. So what is this input? This input I don't know, q bar that is. Now this q output, okay, is what actually? Now it will depend on q bar. Q bar I don't know. Now to find out the q bar, what will happen is I should know, okay, this S is already there. Then the other input is nothing but q. That is, output is depending on itself. So in these cases, what we have to do is we have to assume some previous value. Okay, that is q1 value. You have to assume previously. So let us assume this q. Let us assume this previously. That is before giving the inputs. Let us assume I didn't give 0 0 inputs. Before giving the inputs, let us say q is 0. Q bar has to be 1 because complement outputs. Let us assume. So this 0 is a qn now. Okay, the present value. Now I am giving s equal to 0, r equal to 0. I am still, okay, fine, and I am watching this whether the output is changing or not after giving the inputs. Before giving the inputs, the q is 0. After giving the inputs, okay, I have to check whether output is changing or not. Let us do the analysis. So s equal to 0, you can just here. Q bar is 1 because output should be complement. So this 1 will go here, look at here. Or just here, this 0 will come here, look at here. So this 0 will come here. This 0 plus 0 is going inside the NOR gate. Okay, what will happen is 0 plus 0 is what? 0. 0 bar is 1. That means this 1 is there itself. This 1 is there itself only, but since the time has passed, I am putting this arrow. So now this 1 will circulate, okay, to NOR gate 2. So this 1 here, look at this 0, 1. So 0 plus 1 is 1. 1 complement is what? 1 complement is 0. That means 0 is there itself only. 0 is changing to 0 means 0 is there only. 0 didn't change, but what has changed? The time has changed. Okay, from qn it has become, okay, qn plus 1. If this, okay, qn is at t naught, then this 0 is at t1. Okay, so this will be, this 0 is qn at time t naught. This 0 will be at qn plus 1 after time t1. That means after some time the 0 will be there only, of course. That's why I am calling qn plus 1 qn. Now just here qn plus 1 is what? Qn. That means the 0 is there itself, it didn't change. Now you take the previous value 1 and if you do analysis again you will get 1. The meaning is when s equal to r equal to 0, both the NOR gates are enabled and the output is the same as the previous value qn. This is what I want to say. If you take 1, again you will get 1. You can do the analysis. Very simple. Now the next case, if s equal to 1, r equal to 1, what will happen to the next value? qn plus 1. So I am just erasing this. Now s equal to 1, r equal to 1. qn can be anything, the previous state. NOR gate 1, NOR gate 2, blindly they will become disabled. You can just say that. NOR gate 1, NOR gate 2 will be disabled. So qn plus 1 will be what? If they are disabled, look at here, q will be what? I told you that when the NOR gate is disabled, directly you can tell the fixed output value, that is 0. q equal to 0, q bar is what? 0. Now see the interesting thing, since both are disabled, I am writing the values, I know this. Okay, what are the values when the NOR gates are disabled? Q equal to 0, this output will be 0. Now see the interesting thing, okay, q equal to 0, q bar is also 0. Is this possible in Boolean algebra? If q equal to 0, q bar equal to 0, this is practically impossible. Why? Because in Boolean algebra or in, okay, switching algebra, if x equal to 0, okay, some Boolean variable x equal to 0, x bar has to be 1. X bar can't be 0. Here q is some Boolean variable. If q equal to 0, q bar has to be 1. But q bar is 0. This is just after all some circuit, okay, some electronic circuit. Okay, so it can work according to its nature. So what I am doing is, so since it is violating the laws of Boolean algebra, whenever I am giving s equal to r equal to 1, look at this, it is violating the laws of Boolean algebra. So this particular combination s equal to r equal to 1 never give to the circuit because it is violating the laws of Boolean algebra. Okay, so any circuit or any device or any logic gate, if it is violating the principles of Boolean algebra, never, okay, use those combinations or never use those, okay, relations. because it will totally collapse the Boolean algebra. Okay, you cannot work on the devices, okay, when they are violating the laws of yes sir, q equal to 0 means q bar has to be 1, but it is violating the law. So that's why never give s equal to r equal to 1. This is a major problem in this circuit. Okay, so s equal to r equal to 1, never give to this circuit, because the output is entering into a different state, unknown state. Why? Because it is violating the laws. So the last state q1 plus 1, we call it, that is whenever s equal to r equal to 1, the output we call it as simply x. X stands for invalid state. This is an invalid state we call, or sometimes we call forbidden state. Forbidden state, or sometimes we call indeterminate state. So all these mean that you are unable to identify the state. Forbidden, you don't know what is the state. Okay, so that means you cannot put here 1 or 0. So simply don't care. X is also not don't care actually. So just simply put x. So don't think this x is 0 or 1. I don't know what is that. It is a forbidden state, invalid state, indeterminate state. We don't know what is it. If you put 1 or 0, that means you are violating the laws of Boolean algebra. Remember this. Now, look at here carefully. Now understand this table. So this table, what you are seeing, okay, so this is a truth table. So for this SR NOR latch, we got this table. So this table is generally called as truth table. The truth table of NOR latch, or sometimes it is called as a function table. Function table, or one more name they call it as a characteristic table. Characteristic table. Okay. So all these are this is nothing but truth table for SR NOR latch. So you can call function table or truth table or characteristic table. Okay. Now let us understand this table clearly. Look at this. When both the logic gates are, when both the NOR gates are enabled, okay, when they are enabled, if s equal to r equal to 0 inputs, s equal to 0, r equal to 0, okay, then we say the memory element is in hold state. This is the word I will give. It is said to be in hold state. If s equal to 0 and r equal to 1, we say the memory element is in reset state. Now when I am calling reset, reset means 0. The circuit is storing 0. Remember this. So when the circuit is storing 0, okay, I am erasing the previous values. Look at here. If s equal to 0, r equal to 0, then we say the circuit is in reset state. Circuit is in reset state means it is storing 0. If I am writing 0 here, it is storing 0. Okay, when it will store 0, if I s equal to 0, r equal to 1, then it is going to store 0. Now, if qn plus 1 is 1, then we say the circuit is storing 1, and we call this as a set state. Set state means bit 1 is stored in the device. Okay, set state. Bit 1 is stored means q is 1. Now see here, and never give s equal to r equal to 1, and this is called as invalid or forbidden state. Never give this. So just ignore the s equal to r equal to 1 for this circuit, because it will violate the laws of Boolean algebra. Now, and one more thing is, you can just here, now remember these two words, set, reset. Set means 1, reset means 0. So set means device is storing 1, that means q equal to 1. Reset means device is storing 0. So remember this, bit 1, bit 0. Now when it is reset and when it is set, look at here, okay, 1, just here, this SR, this S stands for set input, these are set input, this is a reset input. S for set, reset, these are input terminals, inputs, and these are state actually. State means what it is storing. So look at here, when the device is set, look at the set input. Set input is high, set input is high, the word high is important. Set input is high, the device is set. And look at this, reset input is high, then the device is reset. Okay, look at this, reset input is high, reset high, reset, set high, the device is set. That's why this device is called as active high SR latch. It is called as active high SR latch. Active high. Why it is called active high? Because if S is high, set input is high, the device will be storing 1 set. If reset is high, the device will store 0 or it will be reset. That's why it is called as active high SR latch. And one thing is, you can just here never give S equal to R equal to 1. The first 3 states Qn 0 1, these three states, these are actually valid states. These are not invalid states, these are valid states. The only invalid state is this last one, S equal to R equal to 1. Never give this S equal to R equal to 1 for this SR NOR latch, else it will go into invalid or useless state. And the first state Qn means what actually? The previous state or present state, which is called as a hold state. That means if you want the device to hold the same state without changing the state, then you give S equal to R equal to 0. The device will hold the same bit, either 0 or 1, whatever it is. Okay, the previous value. So the next value will be always previous value. The bit is not changing. That is the meaning of the first thing. Now, one more logic you have to remember. Whenever you are handling, remember, whether these can be NOR gates or NAND gates. If both the logic gates, whether NAND or NOR, if both are enabled, remember this, if both are enabled, it will move into hold state. Look at this, the first case. If both the logic gates are enabled, remember, the device will enter into a hold state, Qn state, remember this. And if both the logic gates are disabled, it will enter into a invalid state. Both disabled, invalid, that is important. Both enabled, previous state. Now, if one logic gate is enabled, other is disabled, it will enter into either set or reset state. You can just hear enable, disable, reset, disable, enable, it will enter into a set state. So these things you have to remember. Both disabled, it will enter into invalid. Both enabled, previous state. One enable, other disabled, it will be in set or reset state. So now what I will do is, I will give a sequence of S and R inputs and I will check what will be the sequence of Q output. So I hope this is clear, right? Enable, disable concept of NAND and NOR. So both you have to remember. So I'll just give a stream of S and R values and then I want to trace what is the Q for this circuit. So S and R are the inputs. Look at here. There is a Qn, okay, or simply I'll call Q. Now 1 0, look at this. If S equal to 1, R equal to 0, what you are getting? Simply you will get 1. This is 1, you can just hear. Okay, that is previous value can be anything, it will be 1. Now what I'll do is, I'll give 0 1. If I give 0 1, you will get what? 0 1, you will get reset. Now, if I give both zeros, if both are zeros, it will enter into the previous state. What is the previous value? Previous value, this is a Qn. So, the same 0 will be. Now, if I give 1 1, what will happen? It will enter into invalid state. Simply put X. Don't write anything, simply put X. Don't put 0 or 1. Now, again I am giving, say 1 0, it will be 1. If I give 0 0, what will happen is, the next state again it will be 1. Now, what I will do is, I will give both ones. If I give both ones, it is don't care. Now, I will give both zeros. Now, you tell me what is output. What will be the Q? If I give 1 1, you know it is invalid for no doubt. If I give 0 0, what will be the next state? The first thing you have to keep in mind is, if S equal to 0 or equal to 0, it is a valid state. That's the first thing you have to keep in mind. I cannot simply keep X here. Okay, it's a previous state is X. So X I don't know what is this 1 or 0. You should not put X equal to 1 or 0. This is not a don't care. Keep that point in mind. It is an invalid state. Some representation. So Qn, you cannot put X. Because if you are putting X, you are moving into invalid state. But actually Qn is a valid state. So you can never put X. If you are putting X means, okay, remember, you are a big fool. So what you do is, now the question is whether you will put 0 or 1. You don't know. It will enter into a valid state. But whether the output is 0 or 1, you don't know. Okay, it will be either 0 or 1. That depends on the delays also. Now remember, the output will be 0 or 1. The exact value you cannot tell as long as the output, as long as you know the delays of this 1 and 2. Remember this point. So next, if I give 0 1, it will be again 0. If I give 1 0, it will be 1. And look at this. If I give 0 0, okay, it will move into the previous state 1. If I give 1 1, it will enter into a don't care. If I give 0 0, remember it will be either 0 or 1. So just be careful with this table. Now this is about, okay, the yes or nor latch.